Okay, we're going to talk about TamStat, which is a statistical program. So anyway, I want to talk about taming statistics. And so basically, this program, in terms of statistics, I'm using Dyalog to do statistics. And generally, there are four different types of statistics, four different types of functions, that we deal with in statistics. The first one would be summary functions, which are basically we take a data set and we calculate we calculate the mean or the standard deviation, things like that. So we basically take a list of values and we come up with a single value. Another type of functions that we have are probability distributions, and these are theoretical models. Oops, sorry. And then we have relations, which these are basically dialogue functions, greater than, less than, and we have logical functions, which and, or, and if, things like that. And so we like to have different types of functions. We put them in, we take families of functions and we're going to treat them in a certain way. Now, summary functions are basically of this form. You just have a y is equal to some function of a whole bunch of numbers, and so that would be your summary functions. When I teach statistics, I usually say, "Can you describe your summer vacation with a single word?" And that's basically what a summary function is. So you would calculate the standard deviation or the mean or something like that. And so basically we just have a bunch of, these are just some definitions of what summary functions are, and they're all structurally equivalent. They're like plus reduction. Structurally they're like plus reduction. And so examples would be like count, mean, or standard deviation. Now, probability distributions, which I'm going to show you some examples of this. We have discrete and continuous distributions, and so those are the two basic kinds. And the right argument is usually a value from the distribution. The left argument would be a parameter list, and a discrete. When we have the discrete distributions, basically, we use the probability mass function. Oops, sorry. And for continuous distribution, we use the density. Now, these aren't terribly useful. The discrete ones could be used, but the continuous distributions are not terribly useful. So we're going to use operators, and I'll show you a little bit later how that works. Okay, so let's see. Relational and logical functions pretty much are the APL functions, and they work pretty much the same way. So I just put those up there for comparison. But here's the interesting thing. We're going to talk about operators in TamStat, and basically we have three values, three types of functions. We have distributions, summary functions, and relational functions. The logical functions I'm not really going to look at this time, but they are used in statistics. But the idea is that we take these various functions and we tie them together using operators. So for example, oops. if we wanted to talk about a distribution, for example, we can take we have the distribution, and then we would have a relational function, and we could calculate from that a probability, or we could calculate the inverse, which is a critical value. And we can also deal with summary functions, and we can deal with hypothesis tests and things like that. And basically, we just take one type of function. We take one type of function and tie it together to another type of function using an operator. And so that's really what we're going to be doing here. And so let's see how this works. So here's an example from probability. What's the probability that you get at least 3 heads in 7 coin tosses? Okay, so we want to figure how to do that. And so if we were to try to do that in R, for example, we would have to use a function called p-binom, which is basically a binomial distribution, and you want 3 heads, but you want at least 3 heads. Well, the way that R sets this up, you have to change that to 2 because you're doing an upper tail, and then you have to take the number of trials, which is 7, and then the probability of success, which is 0.12, assuming a fair coin, and then we have to say, okay, we want lower tail equal false. Okay, so there's a bit of work there, and if you look at that, it doesn't just jump out at you as to what you want to do. So in APL, we just type in 7.05. Those are the parameters. Binomial probability greater than or equal to 3. Now, let's take a look and see what's going on here. This basically reads, I think it reads pretty straightforward. You don't really even need to know what an operator is to understand what's going on. But if we take a look here, you can see that we have the parameters as the left argument, and then you have probability is the operator. The left operand is binomial, the right operand is greater than or equal to, and on the right is the value that's of interest. And so if you were to type that in, you would come up with a probability. So what I want to do is let's go into, I'm going to give you a demonstration of TamStat and see how that works. Okay, this is the TamStat screen, and basically if you want to you could simply we're going to go to probability and distribution wizard. And now what you're going to do is you're going to basically we have a screen here, and you can select the distribution. So in this case, we want to select the binomial distribution, which is right here, and we want probability, and we want to say greater than or equal to, and then we would put in 3. And then we want for the parameters, we want we do 7 trials, and 150 would be the 50% would be the probability of success. Okay, and so you can see over here. This is the expression that we showed you before, and you can see we would have about a 77% chance of getting exactly 3 successes or 3 heads in 7. And then here's a little graph which will show you the green is greater than or equal to 3. Okay. And so this is what we're interested in. So the probability that we get at least 3 heads, okay, would be about 77%. If we wanted to get exactly 3 heads, we just change this less than or equal to equal to, and it would be about 27% or 0.27. Okay, so this is the way this thing works, and we can we can take a different distribution, like, for instance, if we want to do the Poisson distribution, and this is a distribution that has no upper limit, okay? And if you're familiar with statistics, you'll know what this is. If you're not, I just want to show you that it works for any distribution. If we want an upper tail distribution, I can just say greater than 3, and that would give you like about 0.73 or something like that, and you can see that it works that way. And so that's the way this works. Now we can also deal with, these were both discrete distributions, but we can talk about continuous distributions. So let's take the normal distribution, and so here we have a list of continuous distributions. And so let's see, normal right here. And now I can say normal distribution. And when you're dealing with a continuous distribution, the function for the normal distribution will give you, is not really meaningful if you say it's equal to something, okay? Because the probability that x is equal to a particular value is actually 0, okay? So we can do a cumulative distribution. So we'll just change that to less than or equal to, let's say, 1.5. And we'll get a value out. Whereas with the density, you don't really, it doesn't really make a lot of sense. So we had to apply an operator in order to get this out. Now the other thing we can do is we can put in real values, like we can do the inverse, for example. If I want to say, well, what is the probability that the normal distribution is, actually not the probability, but we want to say that the distribution is, hang on a second, we can say the critical value, which is less than 5% of all values, and that would give you the value of 1.645, okay? So this is the inverse distribution, so we can do it that way. And we can also put in real values, like supposing you see that the parameter list changes when you change the distribution, so you know what to put in. So we would put in, let's say, the average height is 68, and let's say the standard deviation is 3 inches, and put that in. And then I could say, well, what's the critical value? And that's the height of the average person that's less than 5% of all the distributions, all the heights. So that would be about a little bit less than 73 inches. And so we can change things there as you want to do that. And so that's how that works. Okay. Let me just continue down the road here. So basically, that's how you deal with distributions. And the other thing we can do is we can generate random variables from a distribution. So for example, I could change normal to random variable, and the sample size is 100, and it will generate 100 different values with that mean and standard deviation. And so there's a little chart there. So if you want to do simulation, you can do that. Okay, the next thing I want to talk about is regression, okay? And so let me just go here and so I have an example. My daughter just got married about 3 weeks ago, and basically I had to pay for the wedding. So I want to take some examples of in order to introduce the concept of regression, I'm going to use an example here. So if we have a wedding here, so you're planning a wedding and it costs $500 to rent the hall and $1,000 per guest. If you have 35 guests, what's the final cost? So I asked my students that. And if you have a budget of 8,000, how many guests can you invite? And supposing the reception hall charges 3,000 for 25 guests and 5,500 for 50 guests, what are the fixed and variable costs? So I asked them these 3 questions. And we go through and we say, okay, we have a model which is f of x is b0 plus b1x. It's a linear problem. And we put in the values. F of x is 500 plus 100x. So with 35 guests, you apply the function, you get $4,000. And so the model is here is, you can just do that with simple arithmetic. So y is equal to f of x. So you don't know y, that's why I put it in red. The second problem, you have to use the inverse problem, okay? Inverse, f to the minus 1, okay? I think the power operator could do that, right? F to the minus 1 of 8,000 is 75, and then you solve that. And in this case, you know y and you don't know, you know y, but you have to find x. And so you have to use algebra, a little bit more complicated. Third step, you have 2 equations and 2 unknowns, and you have to find the slope and the intercept. And if you have, so you want to find b0 and b1. But if you have 3 or more equations, you have to find the best fit. And so you can't always find a solution for all the values there. So you have 3 or more equations. So that's where regression comes in. So in regression, you know y and you know x, but you don't know f. And so my regression function, you input y and x, and it creates a namespace, and in that namespace is a function, which is f. Okay, so that's the way regression works in TamStat. So let's go to TamStat. And so I'll go to advanced regression here. And actually what I want to do here is, here's an example. So you're investigating a murder. You find a bloody footprint size 9.5 near the body. What's the height of the suspect? If the subject is known to be male, would it change anything? So we want to address that. So we're going to take data where I know y is the value I don't know. I mean, I know the value. I have a bunch of heights for students, and I have a bunch of shoe sizes. So we'll select shoe size. And I want to create a regression model from that. So what do? You put heights for y, and you put shoe size for the x's. You hit regress, and here it creates a graphic to show you the slope and the intercept. And over here, it gives you a regression equation, and which is 5.771 plus 1.77 times shoe size. And so that's the regression model. And if you know the guy has a 9.5 foot shoe, what you do is we go to predict, and then I type in the shoe size, 9.5, and I press enter, and it should take a minute here, and then it gives you the point estimate is 60. The guy would be about the suspect would be about 67.6 inches, but that's the actual the best value or the most likely value. But since it's from a sample, might be between. We actually have what we call a confidence interval for the average height and a prediction interval for the actual individual height. And so we create a confidence interval and a prediction interval based on that. Now, if we go back to regress, suppose we didn't say anything about whether the person was male or female. So basically, we can add. We assume that it was a male shoe. So we would say select sex equals male. And then we would hit enter. Oops. sorry, EQ, sorry, this will work. And then it gives you the new model, so that we have two inputs, 1.4 times shoe size plus 2.9 times male, and then we can predict that by simply putting in the shoe size is 9.5, and sex equals male becomes 1, and then we print that, we indicate that. And it should take a minute and it'll come up. Oops, let's see. Oh, there's a comma, sorry. Thank you. There it is. Okay, so now we get it. This is multiple regression. We have two inputs and so on. Okay, so now the next thing I want to show you is just a little bit of graphics here. So we go to descriptive statistics and we hit the graphics here. And you can create things like, with the graphics, we can use chart plot. We've developed it with chart plot, so we have, I can just generate a pie chart by taking some character input. So for instance, pie chart by state, and it lists all the different various states. Most are from Pennsylvania at the University of Scranton, so you see that's the largest one there. And we can do, another one we could do is we could do a bar chart. And we could, let's say we'll take a political party and then group it by sex, male and female, and we can create a bar chart like that. Another one is we want to use quantitative data. We can generate a histogram of heights, okay? So I just select histogram of heights. Or I can create another interesting one is a box plot of height, so we'll do that. Oops, that's not the one I want, height. So there's a box plot of height. And if you want to break it up by, let's say male and female, so we will group it by sex. You can compare the two sexes on the same scale and everything. So that's a thing that works there. And I want to show one more thing. We can do statistical inference. For instance, if I wanted to do a hypothesis test, and I would select, I want to say height. I want to test the hypothesis that the average height is 67 inches. And you can see immediately, you see thumbs down, that's not true. And you can see we reject the null hypothesis. The p-value up there is less than 0.05. Now we can also, if we also wanted to test it, a different case, let's say I want to test the fact that the mean hypothesis is greater than or equal to 69 inches. I can hit that and make that 69, and we get a thumbs up. And so this is a way you can test hypothesis tests. And one of the things I did when I teach my statistics class is you see that there's a lot of moving parts in hypothesis tests. And the idea is that this report is set up in a 2x2 grid where you have, basically you start out from the data, you calculate the test statistic, which is right here, and you usually pick a value for the significance level. It's usually 0.05, but it can be 0.01 or 10% or something like that. And you have these two values, but you can't directly compare this one with this one. So you have to calculate the p-value from the test statistic, and you calculate the critical value from the significance level. And those calculations are based on the probability functions that we have, but they're embedded in this. And so what you do is you calculate across and you compare down. And that's the way I teach hypothesis tests. Okay, so that's that's basically what we have there. So there's a lot more. Michael Bass is going to talk about some other things with this as well. But basically, that's just a sort of an introduction to TamStat. Now, there's also a version of TamStat that we have a desktop version and a version that just runs as a workspace, so you can actually get into it if you want to be able to use these functions in your code and everything. In addition to that, I have a connection to, hang on a second. I've developed an R interface using RConnect, so in some things you can actually have TamStat call R to do the calculations. TamStat will be available to, eventually will be available to Dyalog APL users, so you'll be able to do that. And I mentioned that I use TamStat in my statistics and decision science classes at the Kenya School of Management at the University of Scranton. And Charles, you asked me about, I think a couple of years ago, about Bayesian statistics. Was that? Bayesian. Yeah. So under advanced topics, I have a wizard for Bayesian statistics, where, and we basically, I have an example here where we have, wait a minute, where is it? You have you want to know whether you have cancer or not, and so the prior the prior distribution. Well, you probably don't want to know, but let's say you have a 3% chance of cancer, so that would be 0.03. Oops.
German keyboard, sorry.
Oh, that's why. Okay. Oh,
no.
How do I do 0.03? Yeah.
In Germany we do
okay,
comma.
This is German. Okay, so we're doing this in German. Okay, and then for the probability you don't have cancer is 0.97. I think that'll work, right? And then you want to the test for cancer is 90% effective, and however, there's a 2% chance. Oh, wait a minute, I got to use the comma again. There's a 2% chance of a false positive. And so you take the test, comes up positive, and you want to know what's the probability you have cancer. Okay, and so you hit calc, and it calculates the joint probability and the marginal probability. And so up here, A is the probability you have cancer, which is 58%, and there's a 41% chance that you don't have cancer, which is surprising, because you would think that if it comes up positive, you would think it's more likely that you have cancer, but there's a good chance you're reversing the condition, and that's basically Bayesian statistics. So, and you can have more than two conditions. You can have two different events. Here it's just cancer or not cancer, but you could have multiple 3, 4, 5, 6, 7 different categories and calculate the Bayesian probability. Finally, I just have this is information if you have any questions about it and you want to contact me. I also have a website, www.tamstat.com. Okay, I guess that's it. Okay.